This is Chapter 5, Lecture number 1, so open up to the beginning of the packet. The periodic table is going to be a main focus now of this chapter. The periodic table is divided into vertical columns, which we call groups. The significance of a group is that it represents the valence electrons of the elements in that group. The valence electrons are the electrons in the outermost shell of the element. So to understand that, we're going to introduce the Bohr model. Electrons are found in specific regions of space outside of the nucleus. For now, we're going to think of them as shells, and each shell can hold a specific number of electrons. It's 2 times the shell number squared. So if we are in the second shell, 2 squared is 4, times 2 is 8. It can hold 8 electrons. So using that equation, the first shell can hold 1 squared is 1, times 2 is 2. The second shell can hold 8. The third shell, 3 squared is 9, times 2 is 18. The fourth shell, 4 squared is 16, times 2 can hold 32 electrons. So to draw a Bohr model, we find the number of electrons for that particular atom or element. So fluorine is atomic number 9. So I'm just going to draw a nucleus with the letter F for fluorine. The first shell can hold 2 of the 9 electrons. The second shell can hold the remaining 7 because the second shell can hold up to 8. We're going to follow a pattern of putting them at 90 degrees from each other. So there takes care of 4, 5, 6, 7. 9 electrons total. 2 in the first shell, 7 in the second shell. Chlorine is atomic number 17. So there are 17 electrons. We can put 2 electrons in the first shell, the maximum it can hold. We can put 8 electrons in the second shell. And now we need a third shell. The third shell can hold 18, but we only have 7 left to distribute. So not too complicated. On page 2, any element in group 1 has 1 valence electron. Any element in group 2 has 2 valence electrons. We're going to skip the transition metals now, and you should be looking at a periodic table. Any element in group 13, we're going to drop the ene part of it, will have 3 valence electrons. So 14 has 4, 15, 5, 16, 6, 17, 7. Any element in group 18 has 8 valence electrons, except for helium. Since it only has 2 electrons total, it only has 2 electrons, which both fill up the first shell. We will explain this next concept in class, but electrons closest to the nucleus have the lowest energy. Electrons farthest from the nucleus have the highest energy. The ground state represents electrons in their lowest energy level available. These are the normal Bohr diagrams, but it's possible that an electron can absorb energy and move into what we call the excited state. It moves to a farther out shell. It's farther from the nucleus. When the electron or electrons return to their normal energy level, They release the absorbed energy as a certain color of light. If an electron absorbs enough energy, it will completely leave the atom. This is called being ionized. So on page 3, a ground state and excited state for hydrogen. So in the ground state, we have one electron, which is in the first shell. Excited state, the hydrogen atom still has one electron, but now it has jumped out of the first shell and gone out to a farther out shell. The electron doesn't stay out there very long, and as it returns to the first shell, it gives off the energy it absorbed as light. So in the electromagnetic spectrum, light only takes this one small part. Radio waves are part of the electromagnetic spectrum, as are X-rays. But what's interesting is that if you take an element and you heat it up so that it burns, and you show that light through a spectroscope, which I'm going to show you in class, we get a series of lines that is unique to that specific element. So when lithium is ignited and we look at its flame through a spectroscope, we get a specific pattern of colored lines, which is different than when we take cadmium and ignite that and look at it through a spectroscope. So these lines can be used as fingerprints to distinguish the individual elements. So here is a mixture of two different elements who were burned and then looked at through a spectroscope. All we have to do is line up the lines with the different elements that it might be. So since the mixture has lines here, and they match up here, we know that strontium was one of the elements in the mixture. But we also see that there are some lines here. And they line up with lithium. So what elements are present in the mixture? Strontium and lithium. So following is a quick video on the electromagnetic spectrum, and in class I'm going to show you a video on bright line spectrum. So that is it for me. Enjoy the video, and we'll see you in class.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at the electromagnetic spectrum. What we see as light is only a small part of the electromagnetic spectrum. The electromagnetic spectrum refers to the many types of radiation released from stars, including our own sun. Electromagnetic radiation travels in waves. Frequency describes how many waves per second a wavelength produces. Wavelength measures the length of an individual wave in meters. Scientists describe the electromagnetic spectrum as a long line. At one end lie radio waves, with the longest wavelengths and lowest frequencies in the spectrum. A single radio wave has the length of a football field. After radio waves come microwaves, which produce more energy due to shorter wavelengths and higher frequencies. Cell phones, radar, and microwave ovens use microwaves. Next comes infrared light. The sun, fire, living creatures, and other heat sources all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum, nestled between infrared and ultraviolet light. Red wavelengths have the lowest frequencies and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally violet, wavelengths shorten and frequencies increase. From visible violet light, we move into ultraviolet frequencies. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburns. Next, X-rays, which pass through soft tissue but not denser materials such as bone, making them valuable for medical tests. X-rays also have security applications such as airport baggage checks. Gamma rays produce even shorter wavelengths, higher frequencies, and more energy. In comparison to the football field-sized wavelengths of radio waves, gamma ray wavelengths are as small as atom nuclei.
For thousands of how-to and advice videos on any topic, visit monkeysee.com.